Fine. So we've already seen how marching cubes can be used to extract isosurfaces in 3D. But there is an ambiguity which may arise while we are performing the marching cubes algorithm. So let's consider these cases. So let's assume that these two cubes are actually adjacent to each other. So this has a particular configuration where the black, bold, filled circles are actually the plus and the others are minus. This is how we get an isosurface here. Um, and the adjacent cube have an isosurface like this. So if you look at this particular, anyways, okay, fine. Mm, right. Yeah. So if you look at this face, which is actually shared between these two cubes, what you see is for this cube, the if you just look at this plane, this face, which is a 2D surface, 2D plane, you see that the isosurfaces which are connected in the left side is actually in this direction, uh, and the isosurface which has actually connected in the other face, then for the other cube is actually in the opposite direction. But what happens is these two isosurfaces are actually supposed to be continued because they are actually sharing the same face. So the isosurface is supposed to be continued, but there's a mismatch between how the isosurfaces are actually drawn in these two faces, despite this face having the same plus minus configuration. So this can lead to a mismatch, and it can lead to a possible hole in the isosurface. So we can look at this in the 2D domain as well. So if you see, the ambiguity mostly arises in cases like this where we have diametrically opposite uh, pluses and minus. This is how we get the isosurface if we opting for one set of joining of the iso points. But you can also always use the other way. You can join the isosurface in the other manner. Then you end up getting a disjoint isosurface. So you eventually get two isosurfaces which are actually disjoint. So this can lead to some artifacts or holes in the isosurface extraction. Yeah. So this is a more systematic way of what the problem is. So we have an ambiguous face. If the face has two diagonally opposite points with the same sign, then this can be joined in two different ways, like this and in this fashion and the opposite fashion. So connecting either way is possible. So how do we decide which way to connect? And that is something which we have to decide. So this arises in 3D also. So there are multiple, our goal is to obtain a consistent triangulation where we have a standard way of obtaining what do you call matching cubes, where we decide how to join the isopoints. There are multiple solutions available to it, but the asymptotic decider by Nielsen and Hammond is one of the popular ways of doing this. Let's look at the asymptotic decider. So the basic principle for the asymptotic decider is, suppose we have a face or a grid like this with four vertices, the vertex values being B01, B0, B11, B00, and B10. Then the the value of the scalar value of any point inside this grid can be computed using this function b of st, using the bilinear interpolation over the faces. Okay, so bilinear interpolation, how do you get the values is 1 minus s into s, b00, b01, b10, b11, 1 minus t into t. So for any s and any t which is actually inside the grid, you can get the corresponding scalar field value as b of st, and that is obtained by this bilinear interpolation. So to get an isocontour surface of B, we have to equate this B of st is equal to some alpha. And it happens that if you equate this to alpha, uh, this this will give hyperbolas. So basically the isocontours of B are hyperbolas. So this is how it is going to look like. We have a 0, 0 here, and we have a 1, 1 here. And these are the asymptotes of the isohyperbolas are actually represented like this. This is the grid. And yeah, these are the hyperbolas of the isosurfaces. And where the hyperbolas go through the cell actually depends upon the values on the corners. So depending on the values of on the corners, the whether the hyperbolas go through the cell or whether hyperbolas are exiting the cell, we get an understanding. So we are interested in the cases where hyperbolas are actually going through the cell. Okay. So how do we use the asymptotic decider? So suppose we have the iso value is alpha, then we have the hyperbolas like this. So this is a plus and a minus, and this is minus. Like, so these are diametrically opposite uh, signed faces, and we have asymptotes, which are actually the lines, the axis lines, and it meets at a particular point. So how the hyperbolas actually vary is initially the hyperbolas. Uh, so we take an alpha value, which is actually between the minus value and the plus value, which is greater than the minus value and less than the plus value. So if we gradually increase the alpha value, what happens is the hyperbola actually takes this kind of an orientation, uh, uh, where is actually kind of covering minuses from both sides. That gradually it comes close and close as we increase the value of alpha. Um, and At one point, it actually converges to the saddle point, and after that, it changes the direction. It takes the other direction. So if the alpha value is less than B of S alpha, ST alpha, S alpha, ST alpha being two specific values, we have the general equation is B of S comma T. S alpha and ST, S alpha and T alpha are the values corresponding to one particular X value. Okay, and if that is less than that, we take this kind of an orientation, uh, where it is actually this is how we connect the iso values. If the value alpha value is greater than B of S alpha T alpha, we take the other orientation for the asymptotic decider. So based on S alpha, B of S alpha T alpha, whether alpha value or the isosurface value which we're trying to obtain, if it's greater or less, we obtain two different orientations. That's how we um, do away with the ambiguity. But here then there's an important question of how do we find S alpha and T alpha. So S alpha and T alpha are the points where the hyperbola actually reaches the saddle point. So what we do is we have the hyperbola equation. For that, we take the partial derivative of that hyperbola with respect to s and put equal to 0. And we take the partial derivative of b of s and t with respect to t and put that equal to 0. So you get expressions of s alpha and t alpha. Once we have S alpha and T alpha, we substitute the values in the function of B of S alpha T alpha, which is obtained using the four vertices where we have the bilinear interpolation. So this is how we get S alpha and T alpha. So using this asymptotic decider, we can actually do away with the ambiguity. Okay, let's stop this.